one more time. This is about path integrals of vector fields along some path. Obviously, it's an open path, but it's sort of unknown. You see here, it's an unknown path, but we know its start point and its end point. Of course, again, this tells us there should be, hopefully, some valid potential. Otherwise, we wouldn't even have a chance to explicitly calculate this integral. So all we know is this is the starting point in space. This is the end point. As you see, this is a three-dimensional case again. So now this is not new, but it's, well, I don't really know. I think we did it once with three dimensions probably a while ago. Anyway, we're looking for a scalar field to be used as a potential for this vector field. How do we do it? Well, this is the method I prefer, or you could say it's the only possibility. In case you don't know your potential, just find it by integration. So if our vector field f vector of x vector equals the gradient of some potential phi of x vector, it must be equal to this unknown potential phi, then differentiated partially with respect to x, to y, or to z, respectively, right? So always take the same scalar function, then take the partial derivative for x, for y, for z, and find the three components of your vector field. That's what we want. But we have to, well, to turn things around, because we don't have phi, right? So this is not new, but I'm not sure whether you recall this way of solving the task. Well, our potential phi of x vector, always the same potential, must be equal to indefinite integral of first vector component along x, or over x. At the same time, it must be the primitive function of the second vector component according to y. And thirdly, it must be the primitive function of the third vector component with respect to z. That's all. So let's just perform an integral of this term integrating over x, or over this term referring to x. Well, it's not hard to do, but please remember, what we're doing here is performing truly partial integration, not integration by parts. This is something different. Instead, we are really taking the integral strictly for one independent variable, ignoring the other ones. Ignoring means leaving them alone, treating them as constants. Okay, 2x integrated for x gets us x squared. No question. You remember, increment the exponent and then divide by the new exponent. So x squared over 2, but times 2 gets x squared. Done. So this one, please note that the factors 2 times y times z squared are treated to be constants. Constant factors stay alive. So x is integrated to be x squared half, and again I can shorten this to be x squared then times y times z squared only. Now remember, we have to allow for an additional additive constant in quotation marks. This is not really a constant, I call it C1, but instead it's a term just dependent, possibly dependent on y and z, but never on x. That's important. This must not depend on x, because if it really explicitly depended on x, it would have a certain x derivative, which would additively appear inside here, which is not the case. So this must not depend on x. That's just an intermediate result. Let's go here. Integrating this for y, okay? So now we see everything inside here is constant with respect to y. So it's just, it's sort of like having a constant to be integrated over some variable. Look, simply like integral 5 dx, and we know the result will be 5x linear function plus c. So that's the same thing, but it looks different. Yeah, that's because we have some, well, you could say some noise inside, some disturbing variables which are not even variable. So just treat them as constants and then say this is a constant times y in the result. This constant x squared z squared just stays there, and then times y plus, as I have explained many times, a possible additive term of x and z, but not dependent on y. So let's just take this as the second intermediate result. Moving on here, then third vector component 2x squared yz to be integrated over z. Now this time, this here is a constant factor, which is 2x squared y. Z is integrated to with the result of z squared half, and we can shorten. So what do we get? X squared y z squared plus third pseudo a constant, which is a term of x and y, but not dependent on z. That's all. But now all these three terms must, you could say yeah, now we must be a little creative. We must find out how to choose these terms in order to get everything right, in order that to find one and only one scalar function phi. But as you see, these terms, which I underlined in green color, are already identical. X squared y z squared, x squared y z squared, x squared y z squared. Wonderful. So this looks like one simple potential for everything. The only problem we have is this additional plus x squared. It might be a problem, but it turns out it is not. Why is it not? Because the second and third line here, or row, allow for a certain term dependent on x and z, or dependent on x and y, respectively. Now, the better, well, let me say this. Let's just assume this term would, in the end, it would just depend on x and not on z, and this one also only on x, not on y. It's much the better for us, because then these might be the same, and they might simply be, let's call them C4 of x. Actually, looking here, I can already predict that these terms, this term will not depend on z, this will not depend on y, but only on x. Both will only depend on x because they are equal to x squared. This is the only way of solving the task, you see? And this one will just be zero, plain zero. If I take this choice, if I say C1 is just zero, C2 is actually something of x, and C3 also just something of x, and this something will be x squared, then everything's fine. Well, I hope this, I don't know, you might take a different way of solving it. Well, what did we say again? We said that this, let me see, yeah, this must not depend on y, and this must not depend on z. So if we use x squared for both of these, everything's fine, because x squared does not depend on y, and it does not depend on z, and that means everything's fine. If you don't believe it, you just test it, right? Because you take this, x squared plus x squared times y times z squared, plus now, I must admit, one real constant, so one number which is not dependent neither on x nor on y nor on z. This must be allowed, of course, but even this can be chosen to be equal to zero arbitrarily. Okay, so we may just, well, we are allowed to use this term as a potential. Well, I might, well, it can be transformed a little bit by just taking x squared outside parentheses, or putting 1 plus y z squared in parentheses. Now this is perhaps a little nicer also to handle then. And as I told you, just test. Take the partial derivative for x, you get 2x plus 2xy z squared, which is exactly the first component of the vector field. Okay? The test doesn't take much time, so you should do it. Partial derivative, partial y derivative will be 0 here, because this is additively constant, and here it will be just linear gets constant. Concerning y, it will be just the term x squared times z squared, which is here. And then thirdly, differentiating for z, this goes away, again, it disappears, and this gets to be 2 times z, and then times x squared times y, so 2 times x squared times y times z, everything's fine. So that was, again, this was, you could say this was the preparation. We found that f is conservative. We may now state that the path integral from point P in space to point Q in space need not to be explicitly calculated, but can instead be evaluated by using the potential function, inserting starting and end point. Here I made a little mistake. I just corrected it some minutes ago. Now, please confirm what I'm doing. I say that I must insert the potential value at the endpoint first and then subtract the value at the starting point. And since the endpoint is given to be Q with the coordinates, look here, 1, 0, 2, this has to be inserted first. So I take phi of 1, 0, 2 minus phi of 3, 1, negative 1 for x, y, z. So let's do so. Here's the potential. 1 for x, 1 squared times, parentheses, 1 plus, now 0 for y and 2 for z, so I get 0 times 2 squared, which is 0. I get simply 1 for this contribution. So this is the starting, it's the end value of the potential, right, at point Q. And then subtracting the starting value by inserting the coordinates of point P, which are 3, 1, negative 1. 3 for x, so this is 3 squared, then 1 plus 1 for y, and times negative 1 squared for z squared. And look here, the squaring removes the minus sign. So inside the parentheses, I have 1 plus 1, which equals 2. Outside, it's a factor of 9. So I have 9 times 2, which is 18. Actually, I get 1 minus 18, which is negative 17. Now, you might be a little confused by this negative result, but it's mathematically and physically absolutely common to get negative results. Why is it, or what does it mean in the mechanical sense? Well, it just means that the work this vector field will carry out by acting on the test body or test particle will be negative, which means that in reality, it's the other way around. It's like sort of the test particle gives some energy back to the field. That's the case, you know. Just imagine a body moving with a certain kinetic energy inside a potential field or a vector field or a force field, right? But now, if this particle must take this path from P to Q, it turns out that its potential function will decrease, does it? Wrong again. From 18 to 1. Yeah, so is it? Yeah, it seems. So in the end, while in a positive case, the field will invest some energy into the body. In this negative case, the body will, well, you could say, give some of its kinetic energy back to the field by, you could say, transforming it to potential energy. So it's not a surprise. It's just a case that is often found. Of course, if we just take the path the other way, in the other direction, starting from Q and ending in P, the result will be positive 70. I don't know if my explanation was quite correct now about potential and kinetic energy, but anyway, the exercise is done. Thanks.